All right, back again, Bayes, quarantine edition. So, can't do our face-to-face normal classroom, but we're going to still carry on with this. So, this works as well. We'll also be doing a review session tomorrow night, just as an announcement. So, I have a little bit of code to show you today as well, and Sierra will put that code up on Slack. And you can play around with it. But where we left off last time is we were talking about model selection techniques, and specifically we went into regularization techniques. So the stochastic search variable selection algorithm is a totally different thing. I will admit that's my favorite thing to do. So different SSVS algorithms, the trouble with them is they're usually a little bit computationally intensive. And on your homework, as you're exploring the SSVS algorithm in these two different methods, you'll notice that the SSVS algorithm needs a lot of iterations to burn itself in. So very computationally intensive. I like that because it's a true full joint estimation, where this is penalizing things. So the regularization techniques are penalizing things in kind of an independent manner. I'll say a little bit more about that in a moment. But what is regularization? It's you've got your objective function and you add a penalty to it. And this penalty has to be positive. This thing will be positive. And increase is a function of the betas. So as the betas get bigger, i.e. they move away from zero, so what I mean by bigger is in magnitude. And so as the betas increase in magnitude, this penalty increases. And so what our goal is to find maybe the argument that minimizes this quantity. So I showed you a couple different variations of this. Ridge, the penalty, looks like this. So it's just these squares, these quadratic forms of the betas. So this puts a lot of penalty on the betas. The contours that we're looking at, what does this penalty function look like? It's a circle. For Lasso, the only difference is this absolute value sign. And that seems like a trivial difference, but you can't do calculus with that. And so you're going to need an iterative algorithm to find the solution for Lasso, where for Ridge, we know how to write down our solution. So for Ridge, our solution, beta hat Ridge, is equal to x transpose x inverse x transpose y. I did that just out of habit. So let me say that one more time. So it's x transpose x invert, and then I'm going to add to this lambda times the identity. So lambda is that creature right there. X transpose y. For Lasso, inverse there. So that's the whole point. So this thing is going to be full rank right in here. So full rank. Why? Because this has full rank. This might not have full rank, so this might not be invertible. So pretty easy to work that out. I'll let you guys go through the details, but you should be able to derive that. You derive x transpose x inverse x transpose y. The argument would be exactly the same. So for Lasso, there's no closed form solution. For Lasso, the betas are non-analytic. So you can't just write it down. is an expression. So we'll just say non-analytic. What I mean by that is we need an algorithm to estimate it. So there's no analytical form of the solution. There's something in the middle also. And so combining these two things together, these two penalty functions, sometimes people like it. So what the circle does is it's kind of this very smooth penalty. You're very smooth as you start moving in over here, so it treats the betas a little bit differently than if you put these little kinks in here. And these kinks in the Lasso solution are going to be driving things to absolute zeros. We need better curtains in here, huh? So somebody just made a comment that the reflection is a bit much. Let's see. That's probably not better. Hopefully it shows up a little bit better on the static video. I'm not sure we're going to be able to do something. The sun is just really bright out there right now, so we'll see if we can work on that for next time.
I'm also writing the notes.
And Sierra is also writing the notes, so she'll have those uploaded for you. Apologies for that. So there's this other solution right here that combines the two penalties, the quadratic penalty and the Lasso solution. So I think people think that this one kind of does a smoothing sort of effect to your betas, and it does that, and it does it in a smooth manner. But we like these little kinks in here because we get actual zeros. So combining both of them together is sometimes advantageous. And usually my impression of what people do is they try them all out and they see which one is better in their application. I like this solution over here. Now I will say a few things about the Bayesian interpretation again. So the Bayesian thinks about this just a little bit differently than the optimizer. So the optimizer is just looking for the argument that minimizes that penalty function, that objective function plus the penalty. But the Bayesian thinks about it slightly differently. The Bayesian, for ridge, regression, Bayesian is, when they say they're doing ridge regression, they're using a prior of the form. So for each one of the beta p's, they place a prior on here, and this prior is going to be 1 over root 2 pi. Pens are failing me today. Let's see if these ones work. Root 2 pi, some parameter in there. So we have to think about that parameter a little bit. E to the minus 1/2 beta p squared over psi squared. So that's just a normal distribution. So the ridge regression solution for the Bayesian is the thing that you've been doing in this class, or maybe you use the conjugate prior. So I'll make a note that this is conjugate. So I guess the Bayesian's been doing ridge all along. For Lasso, the prior that we're playing around with is going to be 1 over 2 I'll say, I'll put it, the parameter I'll use it as psi again, e to the minus psi absolute value beta p. And so these parameters right here are the regularizing parameters for the Bayesian. They're not exactly the same thing as the lambdas written down in this form, but they're related to the lambdas. And so if I go to optimize and maybe get the map solution under these two priors, I can come up with an equivalent solution by phrasing it using this penalty system. And so same thing. So regularizers for optimizers are Bayesian's priors. There's some prior that matches it. So think about what a Bayesian's always doing. They're looking at the likelihood function and they're adding some penalty to everything. And that's coming in through the prior. So the question is how do you evaluate the solution on Lasso? How do you do this? And how do you even pick these parameters in the first place? How do you pick the regularizing parameter? And there's a kind of a simple thing that people do, and they cross-validate. So if you don't know what this is, I'll just take a moment, show you what it is, and then I'd like to demo some of this for you. And I will say that there's a Gibbs sampling formulation that the Bayesian will use in Lasso, and I put a paper up for you online, and maybe we can glance at that paper real quickly next time when my computer's operational. So there's just one interesting equation in there, but there's a nice way to build a Gibbs sampler to deal with this case. Pretty efficient. Obviously, working out the solution in Ridge is almost instantaneous. So it just depends, how much do you want those zeros? So cross-validation. Now, I have heard people say Bayesians aren't allowed to cross-validate because it's a frequentist technique. And it's true, it is a frequentist technique. But I'm not sure I buy the argument that we can't do that. So the whole point is that we can't estimate that just directly because it doesn't have any data in here. These are just priors. So you might say, we'll put a prior distribution on one of these parameters right here, but you still have the same problem at the next step of everything. So you have to do something to come up with what is the right penalty that we're going to place on the betas. So cross-validation, frequentist technique, definitely not a Bayesian technique, but still useful. So I'm just going to illustrate this for you. Let's imagine you have your data. So I'm going to say my y's are here. So my y's are here, and my x's are here. And so what I'm going to do is I'm going to break up this data set. So this might be maybe large number of n right down here. So this is 1 all the way down to n. So we've got a lot of data to play around with. I'm kind of presupposing we have a lot of data. If we don't have a lot of data, cross-validation can be problematic. So I'm going to assume that this is relatively high. There's a lot of cross-validation strategies. We'll talk about 1 or 2 of them. But what we're going to do is we're going to break this data set up. So I'm going to say I'm going to come up with y, and I'm just going to give them some names. I'm going to say this is y training. And then I'm going to have y test. And then I'm going to have the corresponding x's as well. So this is x train. And this is going to be x test. So all I've done is basically just broken this apart. Now the question is going to be, how do you pick which data points to go into the two different groups? And that's the whole thing of different techniques in cross-validation. So I wouldn't suggest split your data set in half the way that I drew it. Instead, what you would probably do is take a good amount of the data and train on everything, almost all of it, like maybe 90%, and then use the rest of it to test. So what we're going to do is we're going to build our model out of this stuff. So from this stuff, we're going to get our beta hat. I'm going to say we're going to do maybe Lasso. So from that data, I get beta hat Lasso from the training data set. So I'll call this, I'll put in a superscript train. And then what we're going to do is we're going to use our test data set. I'm going to take this solution that we just got that we used, where we used this data to build that solution, and then I'm going to compare how well the model formulation under the training data predicts this y. So what we're going to do is we're going to come up with y predicted. So you might call this y hat sometimes. And this is going to be equal to x beta lasso train. So I've just taken this solution and I plugged it in right here. What x's am I going to use? I'm going to use the test x's. So those are these x's. So I haven't used this yet. So what we're going to do is we're going to compare y hat predicted to y test. So this is that stuff. This one is that. And so what we're going to do is we're going to keep repeating this process, and we're going to move around these parameters. And we're going to see what set of values, our regularizing parameters, lead to good predictions. And so that's kind of the name of the game. And I like that because I like to look at predictive performance on things. So there's other criterions people will use, model fit. That's like the BIC thing or the AIC thing. But this is quite a bit different right here. This is heavily computational. They used to have different names for this, like jackknife was, I guess that's a little bit different. So I'm just going to refrain from going down that. Similar to it. So anyway, this is what cross-validation is. But we're not just going to do it once. We're going to repeat this process. So we're going to repeat lots of times. Repeat. And see how you do on average. And it's kind of nice. Computers like to do this stuff for us. So this would be incredibly tedious. So I would reach into this data set at random, and this is the way that I'm going to demo it to you. I'm going to reach into the data set at random, and I'm going to create these two groups of data. And then I'm going to check to see how well I've done. Now, how we compare, there's lots of ways. I'm going to show you the mean squared error technique for doing it. So, but it depends on what you're working in, what is your objective. So, would probably dictate how you compare. But the comparison might be something like this. MSE, where that's just sum of the y predicted minus, and then I've got a whole bunch of these, so I'm just going to say I goes from 1 to the number in my test set. Just however many data points are here. And I'm going to compare that to y test. I'll have the ith index right there, square this thing out, and divide by the number in your test set, however big this is. So this is number in the test set. Now, very typically what people will do is I'll do something like tenfold cross-validation. So cross-validation has a lot of different names, but they might do something like randomly grabbing 10 data points from here, throwing it into the test set, and then taking all the remaining data points over here. So if you were very data rich, maybe you could just chop the data set in half and only do this a couple times. But if you were data poor, then you would be inclined to just use a little bit of data over here and a lot of data over here and just repeat that over and over again. We have a question, so I'm going to read it. Okay, so somebody said for the homework set, there was one data set that I gave you that only has 50 data points. So that's not huge. But a good strategy might be to do something like tenfold cross-validation. So you could reach into your data set, grab 10 points at random, and you'd still have 40 data points to train everything. Now, of course, if p is bigger than 40, this isn't going to work very good. But saying that, regularization techniques still can work in those cases. So what you might do is just drop it down to fivefold cross-validation and repeat that process over and over and over again. And people would do it in data sets of 50 data points. So you'll tell me how well it works. So, and you'll be able to tell if your techniques are working well if you use slightly different techniques and they yield similar answers. And so what I really want you to see on the homework is that in that data set, the different techniques will lead to different answers. And so the question would be, could we really figure out what the model is? And the answer is probably not. So I might say you might get about 80% of the way there. I think that's maybe about how well Lasso was working when I tried it out. That it's like the answers overlaps the true model with 80% of the variables that we pull out that are non-zeros. So yeah, it is what it is. So you got to just try it out, check it out, and see how well it works, but you'll make a comment about that as well. The data sets are in increasing order of difficulty. So the first data set, you should be able to recover that model. For the second data set and the third one, probably not. And you'll know what I mean once you code up all this stuff and do the comparisons. So that's just a little bit of a heads up. So let me demo this and show you what it actually looks like in practice. So we're going to switch over to MATLAB and use the projector for a moment. We can't see that at all, can we? That is really rough. Can you change the... You guys cannot see that, can you?
We can barely see anything. That background is confusing.
Hold on. Let's color. Just no default color.
Much better now.
Make the font bigger too.
I know, I'm getting there.
Sweet.
Does that help you guys?
I believe they can see that.
Better?
Yes, that's it.
Awesome.
Okay, so back in the day, coding this up and doing the optimization would have been a challenge in itself, but we're fortunate enough that we have friends over at MathWorks that build us software. There's a lot of software packages that will do this. You can find it for free in R. On campus, the MATLAB licenses are pretty cheap. So if you're in an industry, getting all these packages to do this would cost some real money. So they're pretty friendly to us over in academia. The reasons for that are fairly obvious. So the developers are academics, and it's a good marketing tool to give things away for super cheap to the workforce. Here's what I'm going to do. I'm just going to generate some data points right here. So I'm going to build a model. So what I've done is I'm generating some random normals. I've got 5 different x's, and I get 100 replicates out of this process. So they're all coming from a normal model. Everything is centered at 0, and the variance is 1 in there with these arguments. I'm going to put some weights in here, and I'm going to weight those x's. So I'm going to multiply these weights into the x's. I have 3 zeros that are plugged in right there. And so my model's only being developed from the x's that pertain to those weights. So I've got a whole bunch of data that I'm going to feed in, and what I want to be able to do is estimate that there's 3 zeros in there, and 2 of the things are non-zeros. And if I can do that, then I'm in pretty good shape. So I generate a little bit more noise. So I'm going to add some more noise to the whole process after I multiply in my weights. So you don't have exactly things zeroed out here. So we're taking those zeros, and now we're going to put some noise all over them. And that's what this is doing. And then I can just invoke the Lasso optimizer in MATLAB. And the code name for that is pretty straightforward. It's called Lasso. You hand it X, you hand it Y, and then you've got a whole bunch of choices on how you want it to choose your lambdas, your regularizing parameters. Cool. So that says do tenfold cross-validation. And then I give it some names right here, and I didn't have to do this, but at the end of the day, you would probably want to have names for all of your variables. It gives you a whole bunch of characteristics, a lot of information. So it gives you your betas, and that's what we're after, but it also tells us a lot of stuff about how well it fits under different lambdas. So what it's going to do is it's going to pick a whole sequence of lambdas, and for every one of those lambdas, it's going to do tenfold cross-validation. How many times does it repeat this? Zillions. So a whole bunch. And we could control that as well, but I think I'm using the default. So I want to run this real quickly. How do I get MATLAB? Oh,
It's
got
kind
it.
of like,
Got it.
you have to like look that way.
Let's see if we can do this. Now I'm going to give you some more stuff. I've got another command down here, and I want to look at the results. So this is a huge data structure that they end up giving you back. Lots of information in there. And it's got a bunch of commands that know what to do with all of that information. So I'm mostly interested in this plot right here. I want to look at the cross-validated results and see how well they're working. So just highlight a little bit more, and then we'll run it. Just do this once, since it's difficult to do.
Are you running the entire script?
So I'm just going to run everything that's in that file. And here's what we end up getting in return. Yeah, there's good. Okay, cool.
Make it
make it real big. So this is the plot that we ended up asking for, called a Lasso plot, and it shows us our cross-validated results. So what it ended up doing is it's showing you the mean squared error. So that says MSE over here if you can't see it. So that's what's being plotted, is the mean squared error as I change lambda. So this is a function of lambda. And they put this on a log scale so we can look really closely at everything. And so it gives us different versions of lambda, and it works out this MSE by cross-validating. And it's doing tenfold cross-validation zillions of times for each lambda. And that happened remarkably fast. So that should impress you that they've done a really good job on coding up this function, because it was almost instantaneous. So what we notice is that the MSE starts decreasing as a function of lambda over here. And so they end up giving you some, at least ideas. I could pick any one of these lambdas and fit my model, but I want low MSE. So I don't want a lot of error in everything. And so what it's suggesting right here is this is where the curve is flattening out. And they're looking at derivatives of that curve. And then they give you some suggestions right here. So they end up picking like a very low MSE value, and they even say, well, maybe you'll just go out a little bit further and see how well you do. I ended up defaulting, and I picked, let's see if I can see this. If we look at the code, I ended up asking for a particular lambda right here, the index lambda that minimizes the MSE. And that's the one I want. So I type in fit info, it's that huge data structure, and I say, give me the index of that particular lambda, because in that data structure, they have all the lambdas that they wanted to touch, that they cross-validated on, and it has its associated MSE as well. So that particular value of lambda was this one right here. The biggest one they ended up suggesting. And our results are also impressive. So these are the betas that we ended up getting back. So I asked it to plot those betas. So with that index right there, give me the betas associated with that index of lambda. So a lot of flexibility and a lot of stuff that you can check. This is working very well. So if you remember the original numbers, it was 0, 2, 0, 3, minus 3, 0. And it recovered the right model for us. And so I like that result. We'll post that code for you. You can play around with it. Maybe do the ridge solution as well. But if you do ridge, you are not going to get absolute zeros in here. And that's the advantage of Lasso. I think with that in mind, I would take a moment and point to the Bayesian incarnation of all of this, the Gibbs Sampler for it. But I think that we'll do that next time, just because we're having so many technological difficulties right now. So I'm going to leave it there for you guys. But what I want you to see is that most of this stuff is coded up. This is just normal Lasso. So we got a question. What is this code doing? Is it doing Bayesian Lasso, or is it doing just the optimization? And this just does the optimization. But keep in mind, that optimization is equivalent to looking at the map estimator under a Laplace prior, or the double exponential prior, whatever you want to call it. So the Bayesian Lasso, if we looked at the map, there would be a corresponding regularizing parameter that would give us that exact same solution. So while this didn't do the full Bayesian thing, it did do something that's equivalent to the Bayesian thing. Now what the Bayesian would give you, if you did do the full-blown Bayesian thing, is it'd also give you a distribution over those numbers. So they're not just giving you one answer, they're giving you a whole distribution of answers. And so we'll look at that Gibbs Sampler next time, and I'll just point to it. But truth be told, most people end up just I think working through just the plain Jane Lasso. The point that I want to convey is that there is a Bayesian interpretation to all of this. So some people might say this is just penalized likelihood. And anytime anybody says that, I think Bayes. So it's equivalent to the Bayesian map, but they didn't actually go through the full-blown thing to create the posterior distribution. So hopefully that makes some sense. Anyway, we'll be back next time, look over that Lasso paper that I posted, and we'll keep going a little bit deeper with model selection. There's a lot to talk about. All right, thanks you guys.